So let's take a look at how we would go about calculating that pH at various points along a titration curve. And so we're going to look at a particular example. We're going to say we have a 0.10 molar sodium hydroxide solution, and we're going to add that to 20 milliliters of a 0.30 molar hydrochloric acid solution at 25 degrees Celsius. So everything is going to be assumed at 25 degrees Celsius. If we're doing a titration because we don't know what the concentration is of our hydrochloric acid, we clearly wouldn't have this number, right? And we'd be working our way backwards to that number. But what we're going to do is we're going to look at, okay, I know what this concentration is. I know how much of it I started with. What would my pH be at various points along the curve? So we know how you would be able to determine something like that. Okay, so if we haven't added anything, 0 milliliters of sodium hydroxide are added, the question is, what's my pH? Well, at that point, it's really just a hydrochloric acid solution, right? There's nothing fancy going on. We have a hydrochloric acid solution. We know its concentration, so we know what the hydronium ion concentration is because it's going to be a 1-to-1 ratio. For every 1 mole of HCl, we get 1 mole of H+. And so I know what the H+ concentration is for that solution. It's going to be 0.30 molar. Well, this is probably the easiest pH calculation we've done so far, which is simply a matter of plugging that into the pH definition, right? So pH is equal to negative log of the H+ concentration. I know what that is. It's 0.30. And so my pH at this point is going to be pretty low, which makes sense, right? We have a strong acid. We only have a strong acid. We haven't reacted any of it away. And so we're going to get 0.52 as the pH before we've started this titration at all. Okay, so low makes sense. Okay, we're good to go there. Okay, so let's see what happens once we start to add some of the sodium hydroxide. So after we've added 10 milliliters of the sodium hydroxide, now what we need to do is we need to figure out what is it that we have left over. Do we have excess hydroxide left over? Do we have excess hydronium ion left over? And then what is the concentration of that thing so that we can figure out what the pH is? So step one is take your balanced chemical equation. And so in this case, we've got our net ionic, we've got our hydroxide, reacting with the H+ to go to water. And so my first step is basically I'm going to set up a reaction table. Now notice this reaction table is in number of moles. Okay, we're not doing a concentration table because we're adding different volumes together, right? So we've got 10 milliliters of the sodium hydroxide solution. We started with 20 milliliters of my hydrochloric acid solution. So I can't simply do this in a molarity kind of way. I have to do this in number of moles. And so for each of these two reactants, I'm going to figure out how many moles of that thing did I have, right? So I have 10 milliliters of sodium hydroxide solution, so that's my 0.0100 liters. I know its concentration is 0.1 molar, so it's 0.10 moles of hydroxide for 1 liter of solution. Calculate that through, and I get 0.0010 moles of hydroxide. Okay, I'm going to do the same thing over here for my hydrochloric acid. And so I've started with 20 milliliters of the hydrochloric acid solution. I know its concentration. So I know I've got 0.30 moles of H+ for every 1 liter of that solution, which tells me I have 0.0060 moles of the H+. Okay, so now the question is, what's going to get reacted first? And so this is kind of a limiting reagent problem here, but it's a pretty simple one because it's a 1-to-1 ratio. Right? So I'm going to use up the one I have the least of. And so I have less of the hydroxide at this point along the titration curve. And so that's the thing that's going to get used up, right? This is a strong acid, strong base reaction. We're going to assume it goes all the way to the product side. And so I'm going to use 0.0010 moles of hydroxide up. So that's going to be my change for the hydroxide. It's a 1-to-1 ratio on my reactants. So that's also the amount of H+ I'm going to use up. So 0.0010 moles of hydronium ion are going to get used up, which means at the end of that reaction, I know what I have left over. I have no hydroxide left over, and I have 0.0050 moles of hydronium ion left over from the hydrochloric acid. Okay, well now I have everything I need to figure out what the pH is. This is my excess, right? This is what I have left over of. In order to turn that into pH though, I need a concentration. And to get a concentration, I need to know what that total volume is. And remember, we had 20 milliliters of the HCl solution, 10 milliliters of the sodium hydroxide solution to give us a total of 30 milliliters. Well, I need that, right? Because I need to know how much H+ is being used up. Or sorry, not how much H+, but how much, what the concentration of the H+ is, and so I need that total volume. So I take the 0.0050 moles of H+, divide it by 0.0300 liters, because that is my current volume, and I get a concentration of 0.17 molar. Well, that's my H plus concentration. So pH is pretty straightforward at this point. It's just a matter of plugging that in. And my pH has gone up a little bit, right? I've used up some of the H plus, but it hasn't really gone up that much. We're in that first part of the titration curve before the pH changes very much. And so at this point, my pH is 0.77. Still really, really acidic, right? I mostly have H plus in solution, but not quite as acidic as it was before I started neutralizing it with the hydroxide. Okay, let's go to 60 milliliters of sodium hydroxide added. So at this point, it's the same process, right? It's just we're going to be at a different point along the curve. So I still have the exact same amount of hydroxide. That part is not, sorry, not the same amount of hydroxide. I have the same amount of hydronium ion. That part's not going to change because I'm not adding more hydrochloric acid during this titration. That part is going to be the same for every one of these points. What's going to change is the hydroxide, right? Because now I have 60 milliliters, same concentration, and so now I have 0.0060 moles of the hydroxide. I also have 0.0060 moles of hydronium ion, and so this is an equal molar situation. I have the exact same amount of both of them, and so if I asked you what the limiting reagent was, you should stall for a second and then say, I don't know, or both, or pick one, right? Because they're both going to get used up the same amount. And so both of them will be completely used up at this particular point in the titration curve. And so I'll have 0 of either one left. So now the question is, okay, how do I calculate the pH then? Well, we're at the equivalence point. It's a strong acid, strong base reaction, so I don't have to worry about hydrolysis. And so I know my H plus concentration, my hydroxide concentration are the same. And at this point, it's all coming from the autoionization of water. And so if we're at 25 degrees Celsius, that's going to be 7.00. If we're at some other temperature, you're going to have to take kW, figure out what the concentration of H plus is from that kW, basically by taking a square root, and plug that into the pH. But if we're at 25 degrees Celsius, which is most of the problems in this chapter, we're neutral, so that makes it 7.00. Okay, let's go one step further. Now we're going to keep adding sodium hydroxide. We're going to go to 80 milliliters. So if I'm at 80 milliliters of sodium hydroxide, again, set up the exact same reaction table. Again, the hydronium ion is exactly the same. It's not changing. I'm not adding any more HCl to this solution. And so the only thing that's changing is the amount of hydroxide that I'm starting with. So I've got my 80 milliliters turned into liters, multiplied by its concentration. So I get 0.0080 moles of the hydroxide. And so now the question is, which one's limiting? Well, the first step, we had hydroxide limiting. The second step, they were both limiting. In this case, it's now the hydronium ion that's the limiting reagent. And so it's going to be that 0.0060 moles of H plus that are going to get used up. Once I've used that up, the reaction has to stop, right? It can't go any further. So I'm going to use up the 0.0060 moles of hydronium ion, which means I can only use up 0.0060 moles of the hydroxide. And so what I'm going to have left is 0.0020 moles of hydroxide and nothing in terms of hydronium ion. And so now this is the thing that's going to determine our pH. You should be able to tell pretty quickly that that means I'm going to have a high pH, right? I'm going to have a basic solution. I have excess hydroxide, and so it's going to be higher than 7. Okay, so in order to figure out what that actually is, I need to take those moles of excess hydroxide divided by total volume. My total volume now was the 20 milliliters I started with, the 80 milliliters that I added to it to give me 100 milliliters total. And so if I take my 0.002 moles of the hydroxide, divide by my 100 milliliters in liters, I end up with 0.020 molar. We've said this whole problem is being done at 25 degrees Celsius. And so at that point, what that means is I can use my pOH pretty quickly to get to a pH. So pOH is negative log of the OH minus concentration, so negative log of 0.020 to give me 1.70. Again, sig figs, 2 digits into my argument gives me 2 digits past the decimal point in my pOH. Since we're at 25 degrees Celsius, this is where that comes into play. I'm going to use the fact that the pH is 14.00 minus the pOH, and so that gives me 12.3. Again, if this were at some temperature other than 25 degrees Celsius, everything up to here stays exactly the same. It's this part that changes. Instead of 14.00, we would need the pKw of whatever temperature we were at. And so that 14 might change to something a little bit different. But the rest of the process would be exactly the same. So sure enough, high pH, that makes sense because what we have in solution is excess hydroxide. So we're going to have a basic solution once we are past that equivalence point. Okay, so let's ask this question. What if we flip this around? What if instead of having sodium hydroxide as our analyte, or sorry, as our titrant, we had hydrochloric acid as the titrant and the sodium hydroxide was the analyte? We don't typically do this with acid-base reactions, primarily because it's easier to get a really good concentration for sodium hydroxide just by weighing out sodium hydroxide and putting it into a volumetric flask. Hydrochloric acid's a little trickier to get a good concentration on, but we could potentially, for some reason, need to do this titration in the opposite way. And if we did this titration in the opposite way, we need to think about what that means. So now we're adding hydrochloric acid as we go along. We're starting with a sodium hydroxide solution, which means we're going to start up here in the basic part, right? Depending on exactly what that concentration was of the sodium hydroxide would determine where exactly on this part of the pH scale we would be, but we're certainly going to be up here in the high pH part of the scale to start with. As we add the hydrochloric acid, it's going to become less and less basic, more and more acidic, until eventually we get to our equivalence point. Our equivalence point will be the same because it would be strong acid, strong base, so we're going to be right at 7 for our equivalence point, assuming we're at 25 degrees Celsius. And then as we get out here to where we have excess hydrochloric acid, we're going to end up needing to be down here in the acid part of the pH scale, because what we're going to essentially have left over is excess hydrochloric acid. And so the curve in that case is going to look more like this. Start at high pH, drop down for our equivalence point until we're at pretty low pH when we basically just have excess titrant. And so our equivalence point is going to be in the same exact location. It's right there at 7, assuming we're at 25 degrees Celsius. And at that point, we could read off the amount of hydrochloric acid we have added to figure out what the sodium hydroxide concentration was at the beginning. So what you would end up doing in the lab here is you would take this data, so you would use your pH meter, you'd put your pH meter into the solution, you would start to take pH data as you added that hydrochloric acid to the mix. You would then use your analysis software to figure out where that steepest slope is. You'd find your equivalence point. From that equivalence point, you would know the volume of your hydrochloric acid. And in this case, if hydrochloric acid is our titrant, we know the concentration of the hydrochloric acid because it's our titrant. It's the thing we know about. So we would use the volume of the hydrochloric acid with that concentration to figure out moles of hydrochloric acid. From there, we would use our balanced chemical equation to figure out how many moles of sodium hydroxide had been in the original solution. And then from there, we would use the original volume of the solution. So this is probably going to be like 20 milliliters or 10 milliliters, depending on what kind of pipette you use, to then figure out what the concentration was of that original sodium hydroxide solution. I'm going to tell you right now, this equation right here that we've seen before, that we have used before, that equation, M1V1 equals M2V2, this is not an appropriate equation. Do not use it, okay? That is a dilution equation, and it's allowed if you're doing dilutions. This is not a situation in which you're doing a dilution. A titration is a chemical reaction, and you need to use this stoichiometry to figure out what your concentration is. If you try to use that dilution equation, especially if you don't have a one-to-one reaction between your reactants and your two reactants, you're going to get the wrong answer. And even if it gives you the right answer, it's giving it to you for all the wrong reasons. Do not use a dilution equation to do something that should be stoichiometry. And so if you're looking at these kinds of problems or doing this in the lab, this is the path you're going to use. You're going to use your volume of your titrant along with its concentration to figure out moles of titrant. Use your chemical equation to figure out moles of analyte. Use the original volume of that analyte to then figure out what the concentration of the analyte was in the first place.